We are unmuted. So I'll give you a 2-minute warning or something.
Yeah, it sounds great. There's less pressure on me than to be on time. I would say, oh, that wasn't my fault.
So today we will get started.
Exactly.
Okay, so over the last few days, I've heard countless people complain to me that the NHFP does not appreciate stellar evolution. But we have something even better for you this morning. So binary, stellar evolution, and populations. And what better way to get us started than Dom Rowan to tell us about quiescent black holes?
Yeah, thank you. I'm going to talk about how we can discover the hidden population of black holes in the Milky Way. We know that massive stars have short lifetimes, they're relatively rare, but they have an outsized influence, for example, in the chemical evolution of the galaxy. This figure is showing us where different elements on the periodic table are created. We know that massive stars are responsible for forming many of the heavy elements through core collapse supernovae or through neutron-star mergers. But there's still a lot we don't know about the late-stage evolution of massive stars. For example, what's the relationship between the initial mass of a star and its final fate as a compact object? Luckily for us, these massive stars have left behind a plethora of compact objects in the galaxy. So if we can discover and characterize them, we might learn more about their massive star progenitors. The majority of black hole and neutron star measurements now come from gravitational wave merger systems. This was a sentence that would not have been true a decade ago. And this figure is showing us all the black holes and neutron stars we measure from LIGO in blue and in orange. And the other primary way we measure black hole masses are in these X-ray binary systems. And these are shown in red and then in yellow for the neutron stars there. But we know the majority of black holes are probably not in these ultra-compact systems or these accreting systems. There's around 100 million or so stellar mass black holes just hanging out in the galaxy. These could be formed from single massive stars, binary systems, whether it's one massive star or two massive stars or one massive star, one lower mass star. Some of these are formed in denser environments like clusters as well. And all these systems are born with some set of initial conditions, some initial mass and metallicity. If it's a binary system, some initial separation. And there's various physical processes that's going to alter the structure and the subsequent evolution of these systems. Things like mass transfer in close binaries, dynamical interactions in clusters that can create new systems or disrupt primordial binaries. And if we have a binary system and the massive star explodes, a kick velocity is imparted onto the compact object. This can disrupt binary systems as well, or at least change the orbital parameters. And so as a result of all these things, there's a few possible outcomes. We talked about these two. We know that gravitational wave mergers, these are extragalactic sources. They're rare. The same is really true for these X-ray binaries. We expect there just to be a few thousand in the entire galaxy. And so instead, the vast majority of the compact objects in the Milky Way will be in either wide, non-interacting binaries. We call them non-interacting because we don't have accretion from the luminous star onto the compact object. Or they'll be isolated, just free-floating black holes hanging out in the galaxy. So if we can discover systems in these latter two groups, we can get a true census of black holes. For the isolated black holes, really our only option is to use microlensing. There's been one black hole detected this way. This is showing the light curve of that event with Ogle. We expect there to be many more, though, in the next few years with Roman's time domain survey of the galactic bulge, so stay tuned for all that. For our stars with black hole companions, our non-interacting systems, there's different observational methods you can use to try to characterize these things. But the most effective so far has been to use Gaia astrometry. There's been 3 black holes detected this way. This is showing the most extreme example. This is a 33 solar mass black hole in a binary system with a low mass star. This was characterized by combining the astrometric orbit from Gaia, this is on the left here, with spectroscopic follow-up and some Gaia RVs as well on the right. And this allows you to estimate the mass of the companion to the star that you do see, which is 33 solar masses. Obviously, we would see such a star in the spectral energy distribution or in the spectrum itself, so it must be a compact object. This is where Gaia Black Hole 3 sits compared to some of the other black holes detected, the other 2 with Gaia astrometry and some other systems detected with different methods, compared to a sample of X-ray binaries, as is shown on the left in black. And the thing that jumps out is that there's not a lot of these non-interacting black hole discoveries. We know they exist. We know they must make up a significant portion of the Milky Way's compact object population, but we're not finding them yet, which is good because it means I still have a job. We expect to find more with Gaia astrometry. The next data release is in late 2026. But we also know that there's other observational methods we can use, perhaps to probe parts of the parameter space that Gaia might not be as effective as detecting. So today I'm going to talk about 2 different methods, aside from Gaia astrometry, that we can use to try to characterize these systems. First, if we're interested in finding shorter period systems, we can combine photometric surveys and spectroscopic radial velocity variability to look for these kind of systems. This is showing an example of a short period binary system. We have a black hole, a red giant star, and this produces periodic photometric variability. This is called ellipsoidal modulation, so the light curve is down there on the bottom right. And of course, these systems are also going to have really large amplitude radial velocity variability. So this is tens of kilometers per second. This is much larger than the types of signals we heard about with the extreme precision RV earlier this week. And so that means you can use large spectroscopic surveys like DESI or Apogee or LAMOS to try to find these things. And that's exactly what we're doing. We're combining photometric surveys and spectroscopic surveys to try to find stars with black hole companions. I can talk about one specific study we did using epoch RVs from Gaia. There is a sample of stars with epoch radial velocities that Gaia has released. This is on long period photometric variables. So we separate out binary systems from pulsating stars by just comparing the radial velocity amplitude to the photometric amplitude. And then if we want to select stars that are most likely to have massive dark companions, the statistic we use is the binary mass function, this f of m quantity. You can kind of think of it as a lower limit or a conservative lower limit on the mass of the companion to these stars. But in general, higher mass function, more interesting for our purposes here. The 2 systems with the largest mass functions that we look at are J0946 and J1640. These are the radial velocity orbits for these 2 stars. Long periods, 100 days, 230 days, and very large amplitude variability. So the mass functions are large, 1.9, 1.2 solar masses. I guess for some comparison, if you have a regular stellar binary, you're typically thinking of mass functions less than about half of a solar mass. These systems are on the giant branch. They're the orange and the blue points here, compared to some of the other targets we looked at in this particular survey. And they also show ellipsoidal variability. So we look at the Gaia light curves and the Assassin light curves as well. We simultaneously model the light curves and the radial velocities from Gaia to estimate the masses of the companions to these red giants. It's about 3.8, 3.7 solar masses for these 2 targets. Now, we don't see a main sequence star in the SED or in the spectrum, so these could be black hole candidates, but before we can confirm them, the thing we really need is high-resolution spectroscopic follow-up. So we submitted a proposal to do this with GHOST on Gemini South, so maybe stay tuned for that. If these two stars turn out to host black hole companions, this is where they sit compared to the other targets we've detected so far. So they're the two green circles here. So they're kind of right on the upper end of this mass gap that separates neutron stars from the least massive black holes. So they would be probing some of the lower mass compact object formation. Okay, now I want to talk about longer period systems. And this is where we've been pioneering direct imaging and interferometry as a unique strategy to try to rapidly vet candidates. And the idea is if we have some star with large amplitude, long period radial velocity variability, and we go out and take a high contrast imaging observation, we have two options. Either we see star 1 and star 2, in which case, it's a regular stellar binary, it doesn't host a black hole, or we see what looks like star 1 orbiting nothing, which is kind of the coolest indirect detection of one of these black holes that we could get. We're using two instruments to do this, SHARC-VIS on the LBT in the north and Gravity on VLTI in the south. I'll talk about one system we observed earlier this year. This is Kappa Velorum. Kappa Velorum is not a Harry Potter spell. It is one of the brightest stars in the southern sky. It's a B star. It's known to be a spectroscopic binary for more than 100 years. And we selected this as an interesting candidate because the orbit has a large projected angular separation, and because the companion mass implied by the radial velocity orbit is large. So on this figure, for this direct imaging strategy, targets towards the upper right are more interesting. With just the radial velocity orbit, we can only place these broad constraints on the companion to this B star. This is showing how the companion mass, the black hole candidate mass, depends on the inclination and on the mass of the B star. So the thing you should take away is that it doesn't really matter. The companion has to be at least 6 solar masses, so it's a great candidate for being a black hole. So we observed this with Gravity earlier this year. The bad news is we see a second star in the very first VLTI observation. The flux ratio is like 0.2 or 0.25 or something. And so that was a little bit disappointing, honestly. We continued observing this, though, because this is really an awesome opportunity to characterize one of the brightest, most nearby massive star binaries. So we have a total of 9 epochs. This is showing the astrometric orbit fit. And this is a simultaneous fit with archival radial velocities. The word archival here, the word archival is a bit of a stretch, and that's because Kappa Velorum was originally observed as part of the D.O. Mills expedition. This was a group of observers at the Lick Observatory in the early 1900s who took their spectrograph on a steamboat down to Chile, hiked up this mountain in Santiago, and set up shop for a few years. And they observed some of the first spectroscopic binaries in the southern sky. Many of these are so bright that they're not targeted by more recent spectroscopic surveys. So we're simultaneously fitting here our Gravity observations from 2025 with epoch radial velocities from 1904 to 1907, which I think is pretty neat. And of course, this means we can characterize the binary really well, can measure the masses, the temperature, the age of the system. But for my purposes, the most interesting thing is, was this a good test of this direct imaging strategy? We saw a second star, but we were able to confirm it's not a black hole in about 1 hour of observation time. We can then say, would we have eventually detected the companion if we just got a ton of high-resolution spectroscopic follow-up? And we find maybe, but it would require hours of observation, and even then, our ability to rule out a luminous companion would be difficult. There's no ambiguity with these direct imaging observations. There's a second star, it's not a black hole. And so we're continuing to target more systems with Gravity in the south and with SHARC-VIS in the north. I think I'm pretty much at time here. Oh yeah, I'm doing well, okay. But I hope I've convinced you that there is a lot of really exciting stuff on the horizon for these black hole searches. It's kind of like the Wild West out here. There's a lot of different detection methods. There's a ton of false positives I didn't really get a chance to talk about. We're using different strategies, large surveys, targeted follow-up, direct imaging, spectroscopic follow-up. And there's really exciting missions on the horizon. With Roman, we expect to find more of these isolated black holes via microlensing, and of course, with the next Gaia data release in late 2026, we'll find perhaps dozens more of these wide binaries with astrometry. So thanks, and I can take any questions.
Thank you very much. We have plenty of time for questions.
Yeah, really nice talk. I want to ask about these false positives. I know that some of the early searches for these non-interacting black holes were, there's a bunch of weird and perverse, but interesting in their own right.
Certainly.
That aren't black holes.
Yeah.
Is that type of contamination well understood, and how to kind of, ready for that possibility and rule it out?
Yeah, so there's been lots of different types of false positives, as Jason alluded to. I think the most difficult to deal with so far has been these rapidly rotating strip stars. So this is the only backup slide that I have. I'm very happy about that. So this is an example of a system that was originally thought to be a black hole. It was called the Unicorn V723 Monoceros. And the reason it was thought to be a single line spectroscopic binary, I guess I should explain the plot. So the top is showing the combined spectrum, the thing we observe at 2 different epochs. And then we use a technique called spectral disentangling to separate out the component stars. And so what we find is that that secondary, instead of being a black hole, is a rapidly rotating star. So it's got these really broad spectral lines that are pretty difficult to detect using standard like cross-correlation methods or something like that. So that's what we're doing with those 2 candidates we found with the Gaia RVs, getting high-resolution spectra to do this and rule out stripped star imposters.
I have a sort of broader question. How this results, if you detect many massive black holes, how they impact our understanding of the evolution of the binaries and picture?
Yes. So I guess the question is, how is this not just like a stamp collecting exercise where it's
Yes,
like, oh, wow,
exactly.
that's cool. Yeah, I think the main thing is there's a lot we don't know about, for example, the natal kicks that are imparted onto compact objects. By combining the population we observe in wide binary systems with the isolated systems, that might give us a really big clue. We don't know what the relative fraction of those things should be. So if we find lots of these non-interacting black holes in relatively compact circular orbits, that could tell us, oh, maybe the kick velocities that are imparted for massive stars and core collapse supernovae are not as large for black holes as they are for neutron stars, for example. Yeah. All right. Thank you.
We do. All right.
Parallelize slightly.
Oh, I see. All right.
Let's see, how do I, is there some folder?
There should be a big, if you close this.
Let's see.
And there you are.
There you go, great.
All right, so next up we have Nicholas Stephen Rhee telling us about cataclysmic variables.
Hi, everyone. So it's been a real pleasure meeting you all over the last few days. For those of you who haven't met me, my name is Nicholas Rhee. I'd like to just sort of kick off this presentation by talking about accreting white dwarfs. So the really cool, observer, romantic sounding word for accreting white dwarfs is cataclysmic variable. And it turns out that the way that cataclysmic variables behave most of the time is that you accrete some mass from some typically hydrogen-rich, low-mass star, an M dwarf basically, onto some white dwarf. And what happens is the hydrogen accumulates until it basically kind of violently burns, and the thinking now is that probably you don't accrete mass very efficiently, if at all, onto the white dwarf itself. And so to first order, you might expect that white dwarfs in cataclysmic variables accreting white dwarfs have similar masses, similar mass distribution to those of isolated white dwarfs. But actually, isolated white dwarfs have masses of about 0.6 solar masses. It turns out cataclysmic variables, they're centered more around 0.8. And moreover, there are basically no what we call like helium white dwarfs that are sort of definitively known to be accreting. So what are helium white dwarfs? They're basically like the stripped versions of red giants. So something like the sun, turns into a red giant, exhausts the hydrogen in its core, and then gets its envelope removed. These are white dwarfs which are basically below about half a solar mass or so, and we don't know of anything like this. And so, this has been a puzzle for quite a while, but it was kind of compellingly proposed that maybe the reason these systems we don't observe them is because they just merge right away. And so for the rest of this talk, I'm just going to sort of entertain the question, what would happen, to the remnant of such a merger? But if you really want a scenario for how this merger might work, it turns out that in lower mass white dwarfs, these nova events can be very long. Right? And so you can imagine that you might have novae that are so long that they're basically like mini common envelope events, and they cause mergers like this. But I'm going to be pretty agnostic. I'm just going to say, what if the merger happens, and we just take as an assumption that you accrete some order unity fraction of the star's mass onto the white dwarf? Well, to first order, something that's kind of inevitable is that the envelope has to puff up, because you basically put all of this hydrogen on top of this dense core. It puffs up and starts to burn hydrogen in a shell. It becomes basically a giant. Actually, structurally, it's very similar to what will happen to a star like the sun, right? So when the sun burns all of the hydrogen in its core, it turns out that when it goes up the red giant branch, it burns hydrogen in a shell around a core of helium, which is degeneracy supported. So basically, the sun is going to one day become a helium white dwarf with hydrogen burning on top of it. That's the picture, but it's not quite the same thing, right? They're unusual red giants because it turns out that when you have a helium white dwarf that just sits out in space and then merges a bit later, it's had plenty of time to cool. And so it turns out that the reheating timescale after you put like a hydrogen burning shell on top of a white dwarf is roughly something like 10 to 100 million years, right? So the lifetime that you might spend on a red giant is like maybe 500 million years or something like that. So this is basically something that the star can very easily remember for forever, basically. And so indeed, you can construct models like this in MESA. So the dashed line here is basically quantities for normal red giant, roughly normal red giant, and really you should be looking at these bottom panels. When the core is about a quarter of a solar mass, this is basically what the profile of the star looks like. And essentially what you see is that in the helium core, you basically have like this isothermal white dwarf-like thing, and then some envelope. But then for a merger remnant, that starts off maybe around here in the red giant branch. The core of the star is originally much cooler, but even as the star gets very close to the tip of the red giant branch, when it's grown to by maybe 0.15 solar masses, the core is still very cold. Right, so that's already pretty strange. So I'm a seismologist, and so one of the first things that I wondered about was basically what these things kind of sound like seismically, right? And so the basic idea behind seismology is basically we can't see inside of stars, boo-hoo. That's how we learn about everything in space, unfortunately. But what we can do is use the fact that stars have oscillations, they have fluid waves that propagate within them, and that can bring information to the surface of the star where we can observe them. So this is really the only way we can be sensitive to internal properties in this very direct way. Stars like red giants have this very nice property that they're what are called solar-like oscillators. Weirdly, they're not anything like the sun, but the way in which they are like the sun is that they have these very extended convective envelopes, and in particular, pretty high Mach number convection at the surface that excites these oscillations in this very stochastic way. This is just an example of what the spectrum of oscillation spectrum of a red giant looks like. Right, so this is basically if you took the light curve, Fourier transformed it, squared it, and you see that there are these regular patterns of modes with sort of centered around this frequency of maximum power. It turns out that this is quite nice because the frequency of maximum power basically is related to the surface gravity, whereas the spacing between these is basically the dynamical frequency of the star. And so it's already very nice. They already have this very nice property that if you measure these two things, you basically know the mass and radius of the star. Great. But red giants also have this very other property where, so I've described basically the properties of pressure modes, which are pressure waves, the kind of waves bringing information from me to you. But there are also low frequency modes which propagate in the core, which are more analogous to like ocean waves if you want a picture, right? And it turns out that for lower red giant stars or red clump stars, those are burning helium, that you actually have sensitivity not only to the pressure modes but also the gravity modes. And if you can measure those, you're basically probing the deep interior of the star, not just the bulk properties. And so that's just communicating this. And so one thing that we seismologists like to do is consider stars on what is called like a propagation diagram. This is a spacing diagram, right? So on the x-axis, you have this delta nu, which again has to do with the dynamical frequency of the star. When you go up the red giant branch, your surface gravity, your mean density decreases a lot. So basically, you start on the right, and then you move towards the left. And so the dashed line is a normal red giant. The y-axis has to do with the core properties. So this is the spacing not between pressure modes but gravity modes. So this is sensitive to things like what the core looks like. And you can see that most of the stars actually lie on this degenerate sequence, right? And this is because basically in red giants the core is calling all of the shots, right? The core basically tells the hydrogen burning shell how hard to burn. The total mass doesn't matter all that much, it turns out. But when you have merger remnants in this red giant stage, they turn out to not lie on this curve, at least not right away. And the reason for that, there are actually a few reasons that set the placement. You can see these curves right here. But the main reason is because cores which have cooled down or colder are slightly smaller, and that turns out to dramatically enhance the burning in the shell. And so these things are actually kind of puffed up relative to a normal red giant with the same core mass. Okay, so that's all very fun, but I think there's an even more interesting behavior that we discovered in this analysis, which is basically the way that the sun is going to evolve. The fate of the sun is that at some point, the star is going up the red giant branch. It has a core which is maybe white dwarf size, envelope which is maybe 200 solar radii. And then at some point, one shell of the star, which is off-center, starts to burn helium at about 10 to the 8 Kelvin. And then you have this very violent runaway called a helium flash. And the reason why this happens is because we might have intuition about stars as being some gas, which follows some ideal gas law, which means if I add energy to them, I increase the temperature and I increase the pressure. But if you're degeneracy supported, then P is rho to the 5/3, and that doesn't depend on temperature. Right? So basically, you keep heating up this core. You keep enhancing the burning rate, but until you lift the degeneracy, that you're basically running away. And it turns out that these stars, of course, they do something very similar if they have enough mass to get to the tip of the red giant branch. Here are just what we call Kippenhahn diagrams. These are basically on the y-axis, you have the mass coordinate within the star. On the x-axis, you have the age of the time, basically the age of the star. I've basically normalized this age to the time of the helium flash. And I've zoomed in around the helium flash, the early parts of it anyway. So the convective zones are in blue. Yellow is the radiative zones where there's not much mixing. And then the burning regions are in red. So on the top is a pretty normal looking red giant star near the tip of the RGB. It's zoomed in around this first helium subflash. And then you can see what happens subsequently is that you end up with a red clump star that has a convective core and some non-degenerate helium core. So as you start to consider more and more extreme merger remnants, those involving higher mass helium white dwarfs, there becomes a point where the helium flash becomes so off-center because the shell that reaches the right temperature is so far, it's just the star is cool, so then the shell that which first reaches 10 to the 8 Kelvin is kind of farther off. And you end up with this weird behavior where a lot of the helium, maybe even 20% of the helium, can get mixed in the envelope. So you end up with, in some cases, like stars which have 50% mass fraction of helium in their envelope instead of 30. And that's pretty strange. It's already pretty strange photometrically, because it turns out that the hydrogen burning shell luminosity goes as like mu to the 7th or something. Right? So you have this divergence in behaviors where you have merger remnants which don't undergo this dredge up, and so they basically evolve very similar to normal core helium burning stars. And then when your when your helium white dwarf is originally like a quarter of a solar mass or more or so, then you start to dredge up helium, and then your star ends up being a lot brighter. So you end up with this region of the HR diagram. So sort of like a still core helium burning, but maybe temperatures maybe brightnesses which look more like an AGB star. They also look seismically unusual. The main reason for this, so the clump stars are this region up here on the top left. And the reason for that is basically these stars are more puffed up relative to what's going on in their cores. And so they get shifted to the left in this diagram. Right? But these are stars that are very strongly coupled to the gravity modes in the core. And so we should be something which is observable. In addition to that, there are strange abundances which you expect if you dredge up 20% of the core. It's not just helium, which is hard to measure, but you can also get a lot of carbon in the envelope. And it turns out you also get weird other species like oxygen 18, neon 22, which turns out to be relevant for the white dwarfs these produce. In these last few seconds or so, I'll say there are, observationally, there are some candidates that we think are promising, nothing super definitive. Again, there's a divergence in behaviors between whether you have this core dredge-up event or not. If you don't, you can basically make red giants that are undermassive, so they would not become red giants in the age of the universe, but you can just make them this way. On the right, you have a star which has some of this similar properties that are kind of evocative of, at least qualitatively, of the behaviors expected for these merger remnants. So, jury's still out, but some promise. Thanks. I'll take any questions.
We still do have a bit of time for questions, so I'm curious as to what.
Can you go back to your period frequency evolution plot?
Sure. This one or the other one?
So, I mean, in the normal part, there's still a lot of scatter of points around that. So
That's right.
how would I be confident in something following one of your tracks that kind of overlaps some of that scatter? Do we need to get more precise measurements with upcoming missions, or what's driving that scatter? Is that
that's a good question. I mean, so I'm not an observer, so I'm not privy to the precise details, but I think most of the time, like these big catalogs of what are called gravity mode period spacings have to do with like some automated procedure which may be kind of victim to like aliasing effects, basically, right? And so this is something which, if you really want to do this well, which there are now more recent catalogs which attempt to do this, you have to kind of do it by hand and like look at these spectra and make sure things are not going badly. I would say most of this scatter, I would assume, is actually not real.
So it's not coming from the model. The model doesn't say there should be that much scatter.
Yeah, right. So so one thing is stars that are above 2 solar masses actually do cross this region of the spacing diagram, and the reason for that is that those stars actually, their cores don't become degenerate on the red giant branch. And so they do pass through that region, but they're kind of suppressed by the IMF, so you don't expect that many of them. And also, this is not clear from this picture, but you also, again, you can seismically measure the masses here, and you can like tell if things are supposed to be in that region or not. Yeah.
Great.
Yeah.
Josh, do you want to ask your question as you come to set up, or?
Oh, yeah. No, I was curious if the way to find these, is there other ways to find these other than astrophysicists models? What do you think? Like, should we look for them in microscopic surveys, or should we do they have any visibility?
Yeah, I do think that spectroscopically would be great because, again, they have these weird chemical signatures. So yeah, that would be a very excellent synergy. All right, thanks. Yes.
So next we will hear from our local anthropologist on transient science.
Yes. Hi, everyone. My name is Viraj. I'm here to tell you about transients from stellar mergers and how stars merging can impact their surrounding environments. Right. So here's my TMU version of a simulation of what a stellar merger looks like. You start with a star. Eventually, the star expands and becomes a giant star. And then if this star has a companion, sometimes that companion might actually find itself in the envelope of the giant star. This is a phase called common envelope evolution in the binary system. And this triggers an in-spiral of the star. So the star very quickly goes and crashes into the core of the first star, the primary star. And this is a violent interaction that releases a bunch of energetic material. And so this can power an energetic electromagnetic eruption. And we can actually see this. So the first time the time domain astronomers saw this, they were like, oh, this looks cool. We need to give it a nice, cool name. And so they went back to their NOVA directory. And they said, OK, this is done, this is done, this is done, this is done. And the name they came up with was a luminous red nova. So what are these luminous red novae? So the prototypical member of this class of transients was this eruption called V1309 SCO that happened in our own galaxy. It was this 7 magnitude brightening of this system in our galaxy. And thanks to the Ogle survey, we had data going back several years to this eruption. And this data actually showed that this was an eclipsing binary with a period of about 1.5 days. And what was even more interesting is that if you measure the period as the onset of the eruption happened, the period actually went down. And so this was like smoking gun signature that this is a eclipsing binary that underwent unstable mass transfer and then came closer and closer until one day it merged and had this huge eruption. In the last decade, because of all the advent of time domain surveys, we have seen extragalactic analogs of this. We don't really have such nice data set. We usually only see the main eruption. And because they're in other galaxies, you get a distance, and so you can have a luminosity and so you can put it on a luminosity timescale plot. So this is a plot that shows the luminosity, how bright an eruption is, as a function of its the characteristic timescale, how long it lasts. And so you have your type 1a supernovae sitting over here, core collapse supernovae are here, classical novae are all the way down here. And what was found that these things lie between, they have luminosities between supernovae and classical novae. And so they're often referred to as these gap transients because they occupy this so-called gap between these two populations. What this also says is that because they are so much fainter, intrinsically lower luminous than core collapse supernovae, they're also more difficult to find. So we find them in a much smaller volume. So we find nowadays time domain surveys are routinely finding hundreds of thousands of supernovae every year, and we only have 2 to 3 luminous red novae every year. And they're more luminous than novae, so that puts the luminous in luminous red novae. But what puts the red in luminous red novae is that these things become very, very red. So their optical emission lasts for maybe 100 to a few hundred days, but their infrared emission really lasts for hundreds to thousands of days, and they persist as really bright infrared sources. And we think this happens because the ejecta are not very energetic around these stellar mergers, so they cool very rapidly. They form a lot of dust, they form a lot of molecules, and so that basically shifts the radiation from the optical to the infrared. How common are they? I said we only find only 2 to 3 per year, but that's most certainly because we can only see them to a much smaller volume. So what we can do is we can actually correct for all the systematic effects and measure a volumetric rate of these events. And so that's what this plot shows. It shows how common versus how bright. And there's a rough correlation between how bright your eruption is and the mass of the primary star. The more massive a primary you have, the more luminous you expect the stellar merger eruption to be. And so I've marked, just for reference, I've marked the local core collapse supernova rate and the brightness that you expect from a 10 solar mass star merging with its primary, roughly. And so at low masses, lower than 10 solar mass mergers, our rate estimates mainly come from the Milky Way. In the last 30 years, there have been 3 eruptions that we think come from stellar mergers that have been identified. The issue is all 3 were identified by amateur astronomers, which is great, but it's kind of very difficult to quantify all the biases associated with these measurements. But that already is telling you that the rate is more, at least an order of magnitude higher than the galactic supernova rate, which is pretty cool. People have tried to look at it with PopSynth, and they find agreement with the low luminosity, with the lower mass rate, but maybe they suggest that the rate falls off at higher masses. And then what we were able to do with this Wiki Transient facility, which is a time domain survey that systematically surveys the sky, and so it's very ideal to construct rates and demographics of different kinds of transients. So we were able to put a measurement on this part of the diagram, and we actually saw that yes, the luminosity function does fall off steeper than the lower mass rate. Not sure what exactly that is telling us. We need improved population synthesis models to figure out what that is. And what my dream is that we can have better population synthesis models, and with the Vera Rubin Observatory that's coming online, which is going to find many, many more of these stellar mergers. So this rate, just for context, this rate had 9 events discovered over a span of 3 years. And that's really not enough if you want to do precision rate measurements. But with the Rubin Observatory, we are going to get hundreds of thousands of these every year. And so with Rubin, we are going to reduce the error bars on these systematically. We now have a much better understanding for what binaries these come from, how their light curves look like. And so we can really feed all of that information into PopSynth models and try to use that to constrain more parameters of common envelope evolution and binary star evolution that produces these mergers. But that's for the future. As an observer, what I saw was that, oh, look, this rate of massive star mergers is actually comparable to the rate of core collapse supernovae. So the exact number is about 70% of the core collapse supernova rate. There are substantial error bars on this number. I'll skip over that for now. But what we have is we have this very dusty eruption, and we have something that is very common. And so can these two somehow work together and produce a lot of dust in the Milky Way, in the universe? And so this goes back to the problem. We still don't understand where all the dust in the universe comes from. We think supernovae, AGB stars, red supergiant stars contribute, but there's a lot of uncertainties. And for a long time, people have tried to look for alternate sources of dust. And maybe these stellar mergers could be these alternate sources of dust. And so we asked this question to JWST in cycle 2, and the paper is now on archive, and hopefully it gets published soon. But here is the archive number if you all want to take a look. And so we got 4 of the best studied luminous red novae, where we know from archival imaging, we know the progenitors, we have very good light curve sampling, and we looked at them with JWST. These things went off, 2 of them went off in 2021, 1 in 2018, and 1 in 2015. So we tried to span as many phases of these mergers as possible. And this is what the data look like. And I'm sure all of us have really nice memories of modeling JWST data, and so I'm going to share mine. So here is an example of what we found. So this is the near infrared data is is a ground-based spectrum taken with Keck, but then we got this mid-infrared spectrum with JWST and longer wavelength imaging with JWST. So when we tried to model this just as a remnant star with a dust shell around it, we were able to fit the near-infrared and the longer wavelength data, but it didn't quite fit this middle data, and it also didn't reproduce all of these bumps that we see in the spectrum, all of these features. And so it turns out if we add, on top of this dust shell, if we add a layer of molecules, yeah. So if we add a layer of oxygen-rich molecules, we can really fit all these bumps really well. So we can fit these bumps in the near-infrared, but then all of these spectral features are really cool. And so the molecules included in this were water vapor, CO, and SiO. These are very common molecules that we see around red supergiant stars in oxygen-rich environments. And so it's pretty cool that what we're seeing around is this really cool inflated supergiant-sized remnant of a stellar merger. However, I was not very happy because there's this like really unconstrained peak over here, and it would be pretty cool if we could have some data to constrain that. And so we went back and looked, and the NEOWISE survey, which turned off last year, but just before it turned off, it actually observed this field, and it turned out the observations were 2 weeks after our JWST observations. And so we were able to get some measurements, and the NEOWISE data lands over here. So that's pretty cool. It's still got very large error bars because this is very faint in the mid-infrared bands, but this is pretty cool. So we do this exercise for all of these 4 objects. For these 2, we are able to get nice constraints on the molecular column depths. For these ones, we don't have spectra, so we just get constraints on their dust compositions. And when you put them on a plot that shows the dust mass against the days since eruption, here is the purple stars show you where they lie. And for comparison, again, I use core collapse supernovae as a benchmark, and these are dust measurements that from JWST for a sample of core collapse supernovae. And you can already see that just by eye, some of these stellar mergers are actually producing even as much dust as these core collapse supernovae. So that's pretty cool. If you fold in the rates, the number turns out to be that the dust produced by these mergers is about 25% of that produced in core collapse supernovae. So it's substantial. This does not take into account any of the dust destruction physics, which we expect will be lower in these stellar mergers because the rejecta are expanding at lower velocities than supernovae. And so these things could actually be viable sources of cosmic dust, and maybe we should start including mergers in our models of dust formation in the universe. But the last puzzle that I'll leave you with is we know that these things are very dusty, and I exclusively spoke about things that were discovered in optical time domain surveys. But what if there's a whole dusty population of these things that we are missing because we are not looking in the infrared? And there is theoretical backing for this. So if you take take an HR diagram and you plot stellar evolutionary tracks, and you color code them based on prescriptions for how much dust you expect to be formed if the star merges with its companion. So if your primary star is a main sequence star, or it's in the Hertzsprung gap, relatively lesser evolved, you don't expect a lot of dust, you expect pretty low dust extinction. But if you're on this side of the diagram where you have giants and supergiant stars, you expect a lot more dust contamination. And then if you take all the luminous red nova progenitors that we know of and you put them on this plot, these are these diamonds over here. They all lie preferentially to this side, perhaps not unsurprisingly, because we have been using optical time domain surveys to find them. There's only one giant star merger that we know of. This was discovered again by the Ogle survey in an archival search, so it's not really been studied super well. But we think that this whole population, we are missing them because we're just not looking. They should come out in the infrared. There should be these, in contrast to these sharp optical transients that you expect for these objects, you expect very slow, dusty, slow infrared brightenings of these stars for when the primary star is on this side. So to search for that, we are now entering the era of infrared time domain survey. So the one that I worked on during my PhD was called WINTER. It stands for the Wide Field Infrared Transient Explorer. It's a 1 meter, 1 square degree field of view camera that operates in the YJH bands. It's located at the Palomar Observatory in Southern California. It uses this new detector technology. So if anyone's interested in that, I'm happy to chat about it. But with this, we found what we think is a slow infrared transient in M31 that could come from a merger of an AGB star. So this was this source. Here's the new WINTER image. Here's an old reference image from UCUT taken in 2014, like 10 years ago. And you can see that this is a star that just brightened very clearly in the J band. And so when we went back, and because this is an M31, even though this is much brighter in the infrared, there are still very deep optical detections on observations. So we see that this star did pretty much nothing for a really long time and then suddenly decided to just jump up. And we think that the energetics, the overall spectroscopic properties really resemble mergers, and we think this is the onset of common envelope evolution in an AGB star. So if you put it on this plot, this is where it lands. So It is way more evolved than the star than the giant merger that we know of. Yeah, just a few weeks ago we confirmed possibly another one. This is an M33, so stay tuned about that. So we're really starting to explore this phase space over here with infrared surveys. Right, so the future is really bright. We have all of these exciting missions coming up, and I will leave that as my summary slide. I'm happy to take any questions.
Can you constrain the composition of dust that is formed close to this LRD?
Yes, we can. So we can for sure we know it's only oxygen-rich dust. It's not carbon-rich dust. For this specific source, I don't think I have a backup slide for this. Yeah, so the most constraints came for this specific source because we see this like really deep silicate absorption feature, right? That comes from silicate absorption dust, and we were able to constrain the composition of like the classic drain and leaf silicates to olivine silicates. So the best fit model that we got for this was 40% drain and leaf silicates, 60% olivine silicates. That was the only model that fit. For the other ones, we think at these phases, like for example over here, we are just still dominated by molecules. So we think there's not enough dust has been formed around these objects for us to have a clear detection that will enable us to constrain the composition for all of these sources. But eventually, if we keep monitoring these, we'll start seeing signatures not just from the molecules but from the dust. And so from the galactic sources, we know that the dust, the oxygen-rich dust sequence starts off by the formation of alumina dust, and then that slowly converts to silicate dust. And so we expect to see similar stuff here as well.
Very nice. Do you have a sense of whether dust modeling for LRN suffers from like the same uncertainty as core-cloud supernovae, where you pretty much play around with the optical depth and hide any size of dust? Because I mean, the usual assumption is that it's optically thin dust in core-cloud supernovae, but I mean that's like a huge uncertainty. So everything that we do in supernova dust estimates are basically lower limit. I don't know if the same problem arises for this, because it's more optically fit.
Yeah, my sense is you don't really see for supernovae, I'm not super familiar with the way people do these measurements, but you never really see these like very deep absorption features, right, in supernovae. It's always optically thin. You either see emission. My sense is because for these sources, because they're so bright and because we see these like very deep absorption features, we have a reasonable idea of what the optical depth is like. We're still seeing probably just the outer layers of the dust. There could still be a lot of dust inside that is being hidden, and we would just never know that. So in principle, yeah, maybe these could be lower limits, but my guess is maybe we are in a slightly better position than in core collapse supernovae, because over here we have like these features which can really tell us about the optical depths of the dust.
It seems more robust because at like that epoch where you're actually seeing the dust emission zone, you have a better constraint than core collapse.
Yeah.
This seems more robust.
Yeah. So yeah, maybe we are in a better position once.
All right, I guess Nadine, you could try asking yours as we transition speakers.
Thanks, Raj. Super awesome talk. I guess sort of a follow-up to Raphael's question. Is it possible for you to, as you continue to observe some of these sources, would it be possible to see where the dust forms?
Like the radial?
Yeah, like can you make some like simple model of like some spherical expansion or something and like see under what conditions the dust could be forming? Like as it from like molecule rich to like dust rich.
Yes, so let's chat about that.
Yes, awesome.
All right, and next we will hear from Vishal on pulsar rockets.
Yeah, hello everyone. My name is Vishal. I am a second-year Einstein Fellow at Columbia, and today I'm going to talk about rockets. So, for a long time, we assumed that neutron stars are basically just bar magnets, which means that they have magnetic fields which is almost completely dipolar, but this might not be true. So, a few years ago, NICER looked at this millisecond pulsar, and what it found was that it has very weird hotspots. So basically, you get hotspots when you have like charged particles. They are accelerated along the magnetic field lines, and when they hit the magnetic poles, they kind of heat them up and they kind of shine somewhat brighter. Typically, what you would expect is that you would get hotspots like on the opposite hemispheres. This is not what we see. What we see is basically, my bad, what we see is basically 2 or 3 hotspots all in the same hemisphere. Now this is like very, very weird. Like one of the hotspot is at least circular, the other one is more elongated and like crescent shape or something. Now this means that pulsars are not simple dipoles. More like they should have very strong quadrupole and octopolar fields. And in fact, it was found that you would need these quadrupole fields to be at least like somewhere between 3 to 10 times stronger than the dipole field itself. Now, which means that these neutron stars, they're way more interesting, they're way more messy, and they're way more complex. Now, I really love this because this means we can get something like electromagnetic rockets. Now, if these magnetic fields, they are messy, they're complex, and they're asymmetric, which means that when they emit radiation, this is also going to be asymmetric. So you get this constant push along the spin direction. And like this could happen, this could take like several months, this could take several hundreds of years, depending on how strong the magnetic field itself is. And actually, these were first proposed in 1975 by Harrison and Tademaru. And basically what they were trying to do is they were trying to explain why we have pulsars which are moving much faster than their progenitors. And they looked at rockets basically in vacuum, and over past several decades, people have been looking at rockets in vacuum. And what they found is like you can get really huge kicks, somewhere between 100 to 1,000 kilometers per second. But this is when reality comes to bite us. Neutron stars are not in vacuum. So they have these magnetospheres where you have plasma kind of following the magnetic field lines. And if you were to look at like force-free electrodynamics, you basically get no rockets at all. What you find is that like this, the force that you get, the stress energy tensor, is basically proportional to the dot product of electromagnetic E dot B basically, which is 0 in force field electrodynamics. So something that worked so beautifully in vacuum, it basically shut down in reality. If you were to, let's say, relax some assumptions, and if you were to have some like E dot B not equals to 0, and this can happen, let's say, if you have weak pulsars, which means like very small magnetic field, so you don't have enough electron-positron like pair production, so you don't have enough charge to support, to cancel the electric fields. In this case, even in this extreme scenario, the maximum you can have is rocket speed of 30 kilometers per second. Now, this is orders of magnitude smaller than what people were predicting some time ago. So to summarize, yes, rockets are possible, but they are suppressed, and they can only happen in like a special class of pulsars. Now let's take this rocket and let's put this in a binary. And what you have is basically a Kepler problem where one of the objects is getting a constant acceleration. Basically, if you were to orbit average things, you can solve this like analytically. And what you find is that the orbital angular momentum and the eccentricity, it starts precessing about the spin axis. So more like the components along the spin axis are conserved, everything else is not. So it's more like the eccentricity starts oscillating. And what happens, the eccentricity magnitude starts oscillating. And what happens is that this means that if you start with very large eccentricity, it will get moderated over longer time. If you start with small eccentricity, it will increase over time. So more like what rockets do is like they give you like a very broad distribution of eccentricities. So we want to find if these rockets actually exist in reality. And the first place we want to look at is Gaia neutron star binary. So Gaia kind of found 21 binaries where one object is neutron star, the other one is like a solar, like a sun-like main sequence object. And like these had orbital periods like 200 to 1,000 days, and they had all moderate eccentricities. And we're going to look at these objects is because like they're slightly weird. So let's look at, to understand this, let's look at this story. So you start with a binary star. One of this star will die and become a neutron star eventually. But At this stage, the progenitor, when it enters the red giant phase, it's going to be way bigger than the orbit itself, which means it will lead to unstable mass transfer, common envelope, and over time, like the two objects, they will inspire in dangerously close, like way below the 100-day limit, which is what Gaia can detect. So what you want is you want to expand them back so that Gaia can detect them, like larger than 100 days. So in this case, what we can do is we can use supernova kicks. So when neutron stars are born, like the explosion, it's not going to be symmetric. You lose mass in one direction, the neutron star gets kicked in the other direction. And along with the mass loss, what this does is it can expand the orbit again. And eventually you might or might not have rocket phase, which kind of changes this eccentricity. But here's the thing. The same this picture, it can explain like why we are seeing the Gaia neutron star binaries at their current separation. But this does not explain the eccentricity. Now the same process, which is expanding the binaries because of mass loss or natal kicks, it's also making these binaries highly eccentric. So for example, this is like the CDF. And this is, if you don't have rockets, this is the distribution of eccentricity. And what you find is that they're very highly eccentric, like 0.99 and something. This is the real data. This is like the distribution of Gaia eccentricities. You can see that they are no way close. Like there's a huge gap, like between like the theory and the observations. You add rockets, it's a perfect match. So this kind of shows like the 90% interval, and like the Gaia falls like right between this. And what's happening is that, like I mentioned earlier, these rockets, they kind of they like provide this gentle push and kind of moderate the eccentricities and bring them from 0.9 to way more moderate value similar to Gaia. The next question is, what's the rocket speed that you need to explain this? And you can just use like a simple Bayesian method. And what we find is that you would need around like at least 30-ish kilometer per second if you want to explain Gaia neutron star binaries using rockets. Now the next question is, do we absolutely need rockets? The answer is no. So if common envelopes do not shrink the two objects, if they're not efficient at this, we can somehow still explain the Gaia eccentricities. If you don't have to expand them during like the mass transfer of supernova, you do not end up with very highly eccentric system. So again, this is like the CDF, and even if you don't have rockets, and if common envelope does not shrink binaries a lot, you can still explain the Gaia binaries. And again, you can find like what's the minimum separation beyond which you would need rockets. And what we find is like if common envelope does not shrink below 1 astronomical units, you're fine. So the key takeaway is, so we are left with two options. Either rockets are absolutely essential to explain Gaia neutron star binaries. And this is very interesting because, like I mentioned earlier, getting rockets in the first place is not easy. You need this very special class of pulsars where magnetic fields are small, but like they're spinning very fast to actually get the rockets in the first place. Or maybe rockets do not exist in reality, and we just don't know enough about the common envelopes themselves, and they do not bring the two objects, they do not shrink the orbits as much as we thought. Thank you.
So we do have plenty of time for questions. Andy?
So then the rockets though are not strong enough to produce the peculiar velocities.
No, not even close.
That's where it quickly came from.
Exactly. Okay. And it was very exciting because like if you have, so I also love rockets because of one thing. So they accelerate the object along the direction of the spin. And this is something we have seen since early 2000s. Like you have, if you look at young pulsars, their spin and their proper motion are in the same direction. And rockets can explain this. For last 20 years, we've been trying to explain this using like normal natal kicks. We still cannot do that. Like we have so many like core collapse simulations, and it's not easy to get spin and kick aligned in this kick alignment from the core collapse simulation. Rockets, on the other hand, like they do this perfectly, but like their magnitudes are so small.
All right. Well.
Yeah. So from the rocket power, or can you determine how asymmetric the poles are, or?
Yes.
Does it tell us something about like other neutron stars and?
Okay, so in this case, like I do not remember what we were assuming is that, but let's say for 30 kilometer per second, like okay, give me. So what we find is that you need 30 kilometer per second rocket speed to explain Gaia-neutron star binaries. And this is actually pretty much very close to the upper limit I was talking about earlier. And in that case, we were assuming like that quadrupole is like 6 to 8 times stronger than the dipole itself. And this is similar to what people are finding with the millisecond pulsar I showed early on, like J0030. So yes, we cannot say anything about. Okay, so what we can say is that the magnetic field should be less than 10 to the power 10 Gauss, but the quadrupole field should be pretty strong.
All right, so let's thank all the speakers again, and bombard all of them with questions over coffee.
We're back at 11:30.
Yeah, back at 11:30.
You were on time to get a full coffee break.